Hello, everybody. Miss Spung Lewis here to go through our lesson 1.2 about linear measure. So, just as a disclaimer, this video is going to cover all of the new material and some, but not all, of the examples from the lesson. So please go ahead and skip ahead to where your class left off and follow along to the best of your ability with your own notes. And remember that the 1.2 homework is posted in our OneNote calendar and it is due on Friday. Okay, so we've got some vocab involved in this particular lesson, what a line segment is, what we mean when we say one point is between another, or this concept of betweenness of points, and what exactly are congruent segments. There is a warm-up here. You'll see this in your notes. If you didn't do this in class, then we're just going to go ahead and skip over it for the purposes of the video. Let's get into our vocab. So the first defined term that we're introducing in this class is a line segment. A line segment is a measurable part of a line, and it's made up of 2 points that we'll refer to as the endpoints, and all of the infinitely many points in between those 2 points. So key phrase here is that this is measurable. There is a length to a line segment. Now, when we name a line segment, there are a couple of things to note. We're only ever going to use the endpoints of the line segment. So for example, we can name the segment here from A to B. We could name this AB. The symbol we're going to use here is just a line, no arrows over top those 2 letters. So that differentiates this from a line versus a line segment. So line segment, again, measurable from one point to the other. Now, this same segment could be BA, also a valid name. The order here does not matter. Just want to call out also another segment we could name here would be all the way from A to C. Now, even though B is in the middle there, we would just name this segment AC or CA. B would not be involved at all in the name. Lastly here, the length or the measure of a segment is denoted in 2 different ways depending on what you end up preferring. And one of those is this little M and then the name of our segment, AB. So that is really read like measure of segment AB. And the other option that I personally use a little bit more just because it's less writing is simply the line segments endpoints, A and B, with no bar over top. So we want to try to keep straight in our minds A, B with an arrow over top, that's a line. And a line in geometry is really considered a thing. It's considered a figure, let's say, a geometric figure. Whereas AB without the arrows on the line here over the letters, that is a segment, a line segment, also a figure. And lastly, AB with nothing over top these letters, this means we're talking about a length, and this means it's a number. AB can be equal to something, whereas segment AB, well, no, can't be equal. It's a thing itself. So we're going to try to keep those things distinct. Okay. We're going to go through one of these practice questions. I'm going to skip over number 1 and jump into number 2, where we are measuring the length of AB using this little ruler, so to speak here. And this is first in inches. We're asked to provide the length in inches. So notice that A is right, it looks like at about 0, and B is here. Where is that exactly? Well, be careful. Inches, these increments in the inches, are not tenths, they are not 20ths, they are 16ths. So B there looks like it's right about 14/16 or 7/8. So our length of AB, we could write this a few different ways, but one way would be 1 7/8 inches. we could put that in decimal form too, which would be 1.875. Now, something I want to include here is a little bit of unit conversion. So let's say we wanted to represent this length of AB in feet. Well, as I hope you know, that there are 12 inches in 1 foot. Okay, so to convert between inches and feet, we're going to use this conversion rate. Now I'm going to show you a process here that looks like some multiplication. It's called dimensional analysis. This can be really helpful as we get into more complicated conversions. What I'm going to do is take my initial, I'm going to take the decimal form, my initial measurement in inches, and I'm going to multiply by a conversion rate. So this looks like a ratio with a numerator and a denominator. In the numerator, I'm going to put the part of my rate with the unit I want to end up with, which is feet, so 1 foot. In the denominator, I'm going to put what that 1 foot is equivalent to in the units I have, so 12 inches. So really, I'm multiplying 1.875 inches by this ratio, 1/12, 1 over 12, which is really the same thing as dividing 1.875 by 12. And that's going to get us, let's see if I remember this from when I was just doing this in class, 1.1565, 1.6525. I should grab my calculator. Okay, please hold. Okay, so we said 1.875 divided by 12. I was close. 1.5625, just to be accurate. That much feet, not a lot of feet. And we could perhaps round that to the nearest hundredth, 2 decimal places, 0.16, let's say, feet. Okay, so just a little bit of practice in unit conversion there, and certainly just measuring. Okay, moving on to this concept of betweenness. You want to find a corner of your notes to write this definition out, because I don't think it made the note guide. Unfortunately, apologies for that. Betweenness, it's a concept that is fairly intuitive. One point is between 2 other points. We can see that on a diagram pretty well. But there's a couple extra features, a couple extra definitions that we can say are true if M is between P and Q, for example. So helpful to draw this diagram in your notes. And let's complete our 2 aspects. M is between P and Q if, and only if, P, M, and Q are all on the same line, or in other words, are collinear. Our fancy math word for being on the same line. They have to be on the same line if we're going to say one is between the other 2. The other aspect here is that, well, with 1 point in between 2 others, we sort of have some smaller segments, and then we have kind of a whole segment. So basically, if M is actually between P and Q, then what has to be true is that those 2 smaller segments' lengths have to add up to the whole segment's length. And we can write that using our notation for length of the segment. PM plus MQ has to be equal to PQ. Okay. The other thing to note is that diagrams are never really going to be drawn to scale in this class unless you're told otherwise, but that pretty much is not going to be true. Everything is not to scale in our class. So just as a heads up to you. Okay. So I'm going to pick one of these to do. I'm going to pick number 2 here to walk through and skip 1 and 3. But in this case, we have a pretty straightforward example of, we can see from the diagram, C is between B and D. So it is true based on the diagram that BC plus CD should add up to the length of BD. What that means for us is we really just need to add 50.4 and 16.8 to get the length of BD. And if we add those together, which you can do by hand, you can do using a calculator, we'll find that the length of BD is 67.2 millimeters. Now, just kind of reference number 3 because it's just ever so slightly different. For number 3 over here, we are asked to figure out the length of one of the smaller segments, but we have the length of the whole segment. So you're just going to end up subtracting the other small segment from the large segment in order to get the length of LM. Just slightly different. Okay, let's talk about another example, another type of problem we'll run into. So I'm going to skip number 5 and just do 4 on this page here. And we are given a description, and it's going to be really helpful to draw the diagram. So we want to figure out the value of x and the length of ST if t is between s and u. I'm going to pause there. So let's draw this out. I'm just going to draw a segment with s and u as the endpoints and t just anywhere in between. Now we're also told that ST is equal to 7x. SU, that's the whole segment, is equal to 45. Okay, and TU is equal to 5x minus 3. So a diagram helps situate what's going on here for us, but the same concept applies. The smaller segments added together should equal our larger segment. So that looks like ST, 7x plus TU, 5x minus 3. Those added together equal the whole segment SU 45. And we can solve this multi-step algebra equation. 7x and 5x together are 12x. We can move 3 to the other side to get 12x equals 48. And lastly, divide both sides by 12 to find that x is equal to 4. Now that's the only part of what we were asked to do. We do still have to figure out ST. Remember, ST is just 7x, so 7 times 4, or 28. Okay. And number 5 is very similar to this. Okay. Let's talk about congruent segments. So we're going to throw in this word congruent. For a lot of the different figures, objects, things that we introduce in geometry. Congruent segments are specifically segments that have the same measure or length. Have the same measure. I'll put slash length, because that's the only thing we can really measure about a line segment. So we will use this symbol in this class a lot. It's a little small here. What it looks like is an equal sign with a squiggle on top. That means congruent. And we're going to write this in between two segments that are congruent to one another. So, for example, down below we have ND and AV. They are both 5 inches, so they have the same length. We can write that ND, segment ND, is congruent to segment AV. So that's what we might call a congruence statement, kind of like an equation, but for things instead of numbers. Another way that we'll see that two segments are congruent is if we have an equal number of tick marks through the segments in the diagram. So our segments are already marked as both being 5 inches, but we might also add like 1 tick mark, for example, between both segments. Or we could say we've got these other segments. I don't even know how long they necessarily are, but I know that they're congruent. So I could say that by marking them with perhaps 2 tick marks through both of them. As long as it's a matching number, you know that those segments are congruent. Okay. So let's expand that just a little bit. For now, we'll say that congruent figures in geometry are figures with generally the same size and shape. The same size and shape. Now, the or here is to capture things like segments, like angles, where we don't really have a shape necessarily to them. So this would be another way of understanding it is that they have the same measure alone, just measure. So that's for segments and angles. Maybe some other stuff later on. So I'll just put etc. Okay, now what else is on this page is just a little bit of a continuation of what I was mentioning earlier. We do get quite picky. Okay, so when we're talking about things being congruent, it is things, it is figures that are congruent to one another. So on the left-hand side here, we have two segments that are congruent, whereas we could alternatively say that their measures are equal to one another. So those are really similar, but ever so slightly different statements. Likewise, on the right-hand side there, we can say numbers are equal. Okay, so then the measures, JK and KL, the lengths are equal. Or of course, we can write equations like we did for betweenness and use equals. Okay. Let's just do one last practice question where I have a congruence statement. I am told that HI and JK are congruent statements, or sorry, congruent segments. I don't know necessarily yet how long they are. Not sure a diagram is super necessary here, but here we go. We are also told the length of HI is equal to 2x minus 6. And the length of JK is equal to 7x minus 4. Okay, and I've gone ahead and used one tick mark through these segments to mark them in the diagram as congruent. Now, if we know that these are congruent segments, then again, we know their measures are equal, which also means their measures 2x plus 6 and 7x minus 4 are equal. So here is another algebraic equation that we can solve. I will go ahead and subtract 2x from both sides to get 6 equals 5x minus 4. And then I'll add 4 to both sides to get 10 is equal to 5x. And divide by 5 to get 2 for the value of x. Now keep an eye out. We were asked to find HI. So we're not quite done. We still need to go back in and say, okay, HI is 2x, well, 2 is equal to x, plus 6, or 4 plus 6, or 10. Okay. Now, if you were interested in checking your work, what could you do? Well, remember, HI and JK are supposed to be congruent, have the same length, so we could always plug x into our other expression and make sure it comes out to the same thing. So 7 times 2 minus 4, or 14 minus 4, is indeed 10. So they are congruent based on our value of x, or we have correctly solved for x. Okay, that is all for this lesson. Again, your homework is posted in OneNote in the calendar. It is due on Friday. And be careful, like for this problem, if the problem is asking you to solve for a length, make sure you do that, not just solve for the value of the variable, but for the length. You might also just be aware that every once in a while these tick marks through segments in the textbook diagrams can be a little tricky to see. So if something is seeming confusing, you might try zooming in on the diagram, and that might help you find something a little bit more easily. Okay, everyone, thank you. Have a good day.